So this is going over the answers to the trends in the periodic table check test. It's going over the answers, and I advise watching a video like this for revision before any Unit 1 test and also your final test. So here are some of the multiple choice questions. Well, first question says, which represents the first ionization energy of fluorine? So ionization energy is the energy needed to remove 1 mole of electrons from 1 mole of atoms in the gaseous state. So we need to check, do we have 1 mole of electrons in each one? We do. Then, do we have everything in the gaseous state? We do. So then what we need to think about is 1 mole of atoms. This one here is the only one where we've got 1 mole of atoms. Remember, atoms do not have a charge. So C is the answer. The second question asks, which of the following atoms has the least attraction for bonding electrons? So attraction for bonding electrons is electronegativity. And if you look up the data booklet, there is a table. So it's the table that has all the ionization energies. There is a column on the very right-hand side which has the electronegativity. And so we're just looking for which one of those elements has the smallest number. So carbon has 2.6. Nitrogen has 3.0, so it's definitely not correct. Phosphorus is 2.2, so it's the lowest so far, which means we can rule out carbon. And the final one is silicon. Silicon is 1.9, that's our lowest one. So that means silicon is our one with the least attraction to bonding electrons. This next question is one that is quite common to get things relating to using ionization energies to work out the overall energy change, and the word enthalpy just means energy. So enthalpy just means something measured in kilojoules per mole. Now if we look at our equation, we have got aluminium that is 1 plus, and it is going to aluminium 3 plus, and there's 2 electrons. This means that 2 different ionizations are happening. Now if it starts off as Al1 plus, it means that it's going to Al2 plus and then to Al3 plus. So Al1 plus to Al2 plus, that's your second ionization energy, and 2 plus to 3 plus is your third ionization energy. Remember, whatever charge you end up with, that's the number of the ionization energy that's happening. So the third takes you to 3 plus, the second takes you to 2 plus. So we are doing the second and the third, which means we are doing this one, and we just add those two together, which if we add them together would give us 4, 5, 6, 2. Now we're getting into our more explaining questions. So we've got a graph, and it's showing us in the dark bars, so the left-hand bar for each element, the covalent radius. And it says the covalent radius, why does it decrease across the period from sodium to chlorine? So it's not asking you to compare sodium to chlorine, it's to explain the overall trend. Now this question's worth 1 mark. For 1 mark, you just need your basic explanation. And as you go from sodium to chlorine, they are the same period, which means we should be thinking about protons. And so if we're thinking about protons, period, protons, you can say there are more protons in the nucleus as you go across, or you can say greater nuclear charge. For 1 mark, that's all you need. If it was for 2 marks, you'd need to say, well, if you have a greater nuclear charge, there is a greater force of attraction for the outer electrons by the nucleus, so they would be pulled closer. But for 1 mark, greater nuclear charge as you go across. Now, this is a 2 mark question, this one, and this one is asking why the covalent radius of sodium is larger than the ionic radius for sodium. And the answer that the SQA wants is, firstly, they want an explanation. So sodium is, its electron arrangement is 2, 8, 1. Na plus is 2, 8. And it's talking about ionic radius. So what is different? So Na has more electron shells. What does that mean? It means Na has more screening effect. So you could use the term shielding effect or screening effect. And so electrons less attracted to nucleus, therefore further away. Therefore further away. As long as you've done this sort of comparison where you've shown that sodium compared it to sodium ion, then as long as you can only, it's fine to talk about one. Sodium has more shells, sodium has more screening, electrons will be less attracted. You need to make sure you're doing a comparison to get the 2 marks, and always mention shells and screening effect together. Right, now here's another graph. Now this time we've got the dark bars are representing the first ionization energy, and the pale grey bar is representing the second ionization energy. Now this is a 1 mark question. Why first ionization energy increases going down a group? So you're going down a group, what you need to think about is shells. So as you go down a group, atoms have more filled electron shells, therefore more screening effect. So if you mention shells, always mention screening effect. More shells, more screening. For 2 marks, you would then go to say that there is less force of attraction, so it takes less energy to remove an electron. Now, this question is a 2 mark question. The 2 mark question always requires more explanation. This is, why is the second ionization energy much greater than the first ionization energy? And the first thing, just like the last longer question, what you need to do is have sodium is what is you're starting with for the first ionization energy. It is 281. Na plus is 28. So you can say Na has more shells, so more screening. Weaker attraction or weaker force of attraction. So easier to remove an electron. You can also say that writing down both of them and then saying everything there can get you the 2 marks. You can also say Na plus I don't know what's happening with my pen here. Sorry, Na plus has stable full outer shell, needs lots of energy to break. Oh, sorry about this. But you always need to have a comparison. The better answer of those two is that sodium has more shells, more screening effect, weaker force of attraction, easier to remove an electron. Write an equation including state symbols for the second ionization energy of magnesium. So the first thing, on your periodic table, magnesium is Mg. Second ionization energy means we end up with Mg2+. And it always has to be in the gaseous state. We are always removing an electron, and that's always going on the right-hand side as a product. And if it's the second ionization energy and we're only dealing with one electron at a time, that means we are starting with Mg+, and again, needs to be in the gaseous state. So it's very easy, particularly with the fact that magnesium has a G in it. Don't forget that you need to put a G in brackets. Remember, the electron goes on the right-hand side and it's always plus, and your charges, second ionization energy means you finish with 2+, which means you start with 1+. Then we had some problem-solving questions, and these were ones that people did seem to struggle with. So the first thing, it asks you to predict the lattice enthalpy for rubidium fluoride. And as we can see, as we go down the groups, it is decreasing. So from here to here, we're dropping by 120. Then we're dropping by 112. So you'd probably be wanting to drop something that is less than 112. So if we go 112 less than this, so 120, 112, I would go something like 90 or 80 less. So you would go somewhere around the 720 to 740 mark for that. It's not the nicest prediction one because there's no real regular formula. That's why there's quite a big range. But it's dropping by less each time. The second question, is asking to link lattice enthalpy to ionic radius. So the first thing is, if we look, a lattice is made of ions. And so the ionic radius is what is going to control the lattice enthalpy. So it's going to be as the ionic radius does something, the lattice enthalpy does something. So we just need to decide what words to describe what happens to the ionic radius and say what happens to the lattice enthalpy. So if we look here, our biggest lattice enthalpy is for fluorine and lithium. And if we look, lithium, sodium, potassium, and rubidium, they're all group 1 elements. And of them, lithium is the smallest one. Fluorine and chlorine are both group 7. Of those, fluorine is the smallest one. So what it appears to be is that the smaller the ionic radius, the larger the lattice enthalpy. And if we look here for rubidium chloride, well, that's our smallest one, and it's made of rubidium, which is the largest one of these four, and chlorine, which is the largest one of these two. So as the ionic radius gets bigger, the lattice enthalpy gets smaller, or vice versa. So I'm going to write, as ionic radius increases, lattice enthalpy decreases. So it's looking at the combination of ions giving rise to the size. And if I do a different color, if we look here, always look at your most extreme ones. As the ion gets bigger, the lattice enthalpy gets smaller, or increases and decreases. Another problem-solving question. So this one tells us radius ratio is radius of positive ion divided by radius of negative ion. And then we've been given two structures, and they've each got a radius ratio. And what we've been asked is to look at page 17. Now that was on the old data booklet. This is actually page 18. Predict the structure of barium oxide. Is it more similar to cesium chloride or more similar to sodium chloride? Well, if we look at ionic radius, so that's the table we have from page 18. If we look for barium, that's our positive ion, so it's going to go on top. So radius ratio is going to be 1:3:5. And then we're looking for oxygen. Well, oxygen is here. That's our negative ion. It's going to be 140. And then in your calculator, if you work that out, that comes out to be around 0.96, which if you look, matches. Therefore, we would say barium oxide, Ba2, is similar to cesium chloride. So 0. As long as your radius ratio, whichever one it's closest to, is going to be the one that it matches. So I know this video is getting close to the 20-minute mark, but we just got the final set of questions to go. What is meant by electronegativity? It is a measure of the attraction an atom or nucleus has for a shared pair of electrons in a covalent bond. Unfortunately, you just have to remember that. A measure of the attraction of a nucleus for a shared pair of electrons in a covalent bond. Next question. Why electronegativity values decrease going down a group? This is 1 mark. So down a group means we should think about shells. So down a group means more filled shells. So more shielding or screening effect. That's all you need to say. Everything going down a group is about shells and screening effect. Everything across a period is about protons and increased nuclear charge. Our final question was one about bonding in the elements. And we were asking about why halogens in group 7, why their boiling points increase. So the halogens, that is fluorine, chlorine, bromine, iodine, etc. So they are diatomic. That's one thing we need to know. Diatomic, and they are covalent molecular. Okay, we need to be able to identify that. Once we know that they are covalent molecular, melting, covalent molecule, melting is related to London dispersion forces. And I'm going to put LDF in brackets, which means for the rest of this question I can write LDF. Melting is related to London dispersion forces. Down a group, London dispersion forces get stronger. Because, well, what makes London dispersion forces get bigger is because the molecules have more electrons. Stronger forces need more energy to break. And that's what means a higher melting point. Oh, boiling point is what I asked for in the question, boiling point. So you have to identify what is the bonding in all the halogens. Well, they're diatomic, so they're covalent molecular. Remember, covalent molecular, think about London dispersion forces. Down a group, the London dispersion forces get stronger because you have more electrons, which means you need more energy. So I know that's quite a long video, but it is important to have experience going over past paper questions and really seeing what the mark schemes are looking for. Hopefully you use this when it comes to revision, and I will see you in the next video.